I'm Ron Petrick. This is joint work with Matthew Crosby at Heriot-Watt University in Edinburgh and Francesco Rovida and Volker Krueger at Aalborg University in Copenhagen. This work is a little bit different from the previous two talks. We're less concerned about path planning and motion planning and more concerned with task planning and high-level mission planning, the assignment of goals to individual robots in a fleet in an industrial application. So in our case, we're interested in this scenario in modern factory automation where in something like a car assembly line, you have a number of cars that are going through the line, but these might be different types of cars. They might be building different models, different types of vehicles. And the parts that need to come to these cars, the parts that are in common, that's an easy problem. The parts are available, they're close to the line, but many of these types of parts that cars that are being delivered have specialized parts. So the kinds of parts that are on a car are going to be different that you have on a truck. And the way that this is standardly done is there's a warehouse or a type of supermarket which is removed from the assembly line, and somebody collects the specific parts and makes sure they're delivered to the assembly line at the right time. So each of these sets of parts that are collected are customized. They're different in some sense, and they're assigned to a particular vehicle that is going through the assembly line. Now currently this task is done by humans in many cases. So these are people that will spend 7-hour shifts lifting parts like this, alternators that weigh a few kilograms, grates, various types of tubes, and just filling boxes with these parts and sending them out to the line. So over the course of a 7-hour shift, some people will spend maybe shift 2 tons worth of equipment, loading them into boxes to send to the assembly line. So this work really looked at, can we automate certain parts of this process? So in our case, we were using a robot system that looked like this. And this is quite a large robot. It's about 2 meters high. It's an industrial forklift which has been outfitted with a grasping arm and some extra equipment for automation. And the basic idea was, well, can we take the human out of the loop and add a robot or a fleet of robots now to collect the parts, load them into these boxes, and then send them out to the assembly line at the right points. So this problem is a common problem in a lot of modern factories, and the process by which the system works is really the same. So the idea is that there's a set of these orders called kitting orders that specify the types of parts, the quantity of parts, what needs to be collected for one of these vehicles, and this is provided by the information systems of the factory. So somebody knows that these parts have to come out at a certain time, and they have to get to the line at a certain time. Now, in our case, the orders need to be assigned to individual robots that we're assuming we have in this robot fleet that's actually going to perform the task of picking the parts and delivering them. Now, the robot is going to have to go through this supermarket, this warehouse, collect the appropriate parts, deliver them in these boxes. And each robot is outfitted with 2 boxes. These are these white boxes here on the platform. 2 boxes so they can fill 2 orders. Now the kitting orders arrive continuously. You sometimes get a number of orders coming in a big chunk, but then there might be a pause and more orders come in, but they're continually arriving. And parts in the supermarket may run out, they need to be replaced. The robots could break down, in which case they might block out of other robots. So we have to plan to not only collect the parts, but have a facility for dealing with some of the obstacles that might arise in this space. So we looked at, first of all, a simplified version of this problem in terms of a very simple type of supermarket where we had racks around the side. the set of empty kits here, the robots in a particular staging area, and the idea is the robots would come, pick up a kit, and then go through the supermarket to pick up the appropriate parts they need, deliver the kits when they're done, and move back to the staging area. Now, in this initial work here, we controlled the route around the supermarket. And the reason for this is the way it's done currently in the factory that we were working with. So they don't worry about humans bumping into each other. They enforce this protocol whereby the humans follow a particular type of loop as they go. So we implemented a version of this in PDDL, and we tested the scalability of the problem. The PDDL was, in this case, was pretty straightforward. There was nothing really special, but we had actions for doing things like getting the kit, moving through from locations in the warehouse, picking objects, placing them in appropriate parts of the bin, and then offloading the boxes when we're done. The goal was encoded in terms of the kitting order, so the parts we were trying to get, the quantities, etc. Now, the interesting result we got from this in the first instance was that treating this as a single agent problem and just passing it to your favorite standard off-the-shelf planner didn't scale very well. So many of the planners we tried, and a lot of these were variants of fast downward running in various modes. The planners couldn't scale past 2 robots. They had a lot of trouble with the problem in this case. So we then started looking at some of the multi-agent planners that were available through the recent DMAP workshops, and in particular planners from the co-DMAP multi-agent planning competition. We used one of our planners, in fact ADP, an agent decomposition planner, which did fairly well in the co-DMAP competition. So ADP finished first, I think, for coverage and third for speed in the competition. And not so surprisingly, it did a good job in this space. So it could easily solve instances with 10 or more robots in this problem. However, when we started looking more closely at the quality of the plans we got, it turned out that they really weren't that good. So ADP's solutions in this case were to really assign everything to a single robot. So a single robot would get the job of completing one bin and then just keep going around and around again to complete all of the missions. And the reason for this, not to go into too many details on the planner, was that it uses a type of greedy assignment. So it selects an agent to perform certain tasks and then greedily assigns certain actions to it. And so in our case, this greedy assignment produced very unbalanced plans for us. So we took a look at seeing if there was a way we could better balance the plans for the set of robots that we were using in this space. So our result was a new planner, a variant of ADP called ADBP, which implemented 3 new types of heuristics. And they're actually very, very simple heuristics that looked at some of the heuristic values we were already generating in the course of the search. And then combining them with some of the other heuristic measures across the set of the robots we were considering. So the max heuristic was simply one that looked at the H value of the state across all of the agents that were being considered. This was a good estimate of make span, but it discarded a lot of information. The total heuristic was one that just simply totaled up the H values from across the agents. And again, this contained a lot of heuristic information, but it wasn't a very good estimate of make span for us in this case. And then finally, the square heuristic tried to take the sum squared total as a type of balance between these 2 extremes. One thing I should say about this is that although we were attempting to kind of balance the plans across the set of agents, we were trading off speed in this case. So the speed of the search was going to go down. But for our particular domain, we thought that was an acceptable trade-off. It was better to have more balanced plans that took a longer time to generate than unbalanced. In terms of the results then from rerunning the simulated scenarios with the more balanced planner, we do produce more balanced plans kind of across the board. This is just a snapshot. There's more details in the paper on some of these results. But the important takeaway message on this part of the work was that the search was much slower, but in our case was kind of good enough. One interesting result was with the max heuristic. It still did marginally better than the standard planners that we tested, but it produced very interesting interleaved plans where essentially each of the robots would take one step and then would go back to the original robot. So robot 1 would take one step, robot 2 would take one step, and so on, and then iterate around. In terms of the plans, what they look like, they look something like this. So they involve moving to kits, picking up appropriate parts with a plan kind of decomposed for each of the robots in the mission. Now, that was the first part of the work, and that work was done in simulation to give us a sense of whether or not we can use these techniques in the real environment. The second part of the work was then putting this onto the real robot system. And in our case, a lot of the structure, the hardware, we had no choice about. The architecture, we had very little choice about. So we were tasked with finding a way to kind of integrate this planning approach within this larger framework. So in our case then, the ADBP acted as a type of mission planner at the top of the system, which processed the kitting orders, made the assignments to the individual robots, and gave them these plans in terms of the task level actions they needed to perform. On each of the robots, though, there was also an onboard task planner. In this case, it was just simply temporal fast downward, which would be used for replanning purposes when things went wrong. But provided everything nothing went wrong, we just used the plans that we were originally generating at the mission planning level. One of the interesting kind of consequences of this work was that at the robot level, the robot level actions, the skills were being implemented with a particular type of skill framework called ski-ROS, which was tightly integrated with the ROS environment. One of the interesting things here was the structure of a robot skill looked very much like a standard planning action. So it had preconditions and effect checks. It had state and parameters coming into the skill, and it was actually implemented at a very high level. So the second piece of work that we did here was really looked at a way of whether or not we could generate the PDDL domain then automatically from the skills that were being presented to us on the robot platform. So in the paper, we have an algorithm for doing this. This is an idea of what some of the skills look like at the high level, at least the interface that's exposed to the high level. And this is the type of PDDL action that we were outputting as a result of this process. The interesting thing, and kind of where the hard work came in, was there was a lot that was very implicit in these skill descriptions. And so we really needed to look at the world model to make explicit certain things in the PDDL. So the fact that the robot could only be in one location at a time was implicit in the skill representation, but we needed to make it explicit in the PDDL representation. So I refer you to the paper for the details on that. Once the system was on board the robot, we were able to test it in the factory. One of the problems we only had one physical robot. So that made mission planning somewhat easy for us. In this case, the task planning was also really fast, so things did go wrong, and we had to replan, mostly due to failures at the skill level. Nothing to do, as far as we could tell, with failures at the mission planning level. So very quickly, I'll show you a little video on this. Where is it? Nope. Yes. sorry, screen again. Fun. Okay. Okay, so this is the robot. We were able to test this in the real factory environment. This is the PSA Peugeot Citroën factory in France. So these are real parts used in the automotive process. So it's a beast of a robot. They also made us slow it down to 50% for safety reasons. So one of the interesting things with this is you actually have a lot of time to do planning and replanning while it's working, because it's not moving that quickly. But anyway, all right. So just to conclude, so this work was really looking at, could we take some of these off-the-shelf tools for doing multi-agent planning, modify them appropriately to use them in this mission and task planning context. So we have a modified version of the ADP planner called ADBP, which does a pretty good job of producing balanced plans. We also have this process for automatically generating the PDDL from this robot skills framework that's available. Future work, we have kind of a blank slate to look at other contexts where we would have multiple robots that could collaborate together for doing things like filling kits. So a robot could pick up 2 parts, give it to its partner to put into its box, for instance. I'd just like to conclude by saying these industrial contexts, I think, are a really good test bed for automated planning. And I don't think enough of us are doing work here. We're particularly interested in things like the planning competition for logistics, robots, and simulation. Ares is sitting here in the front row. And I would commend these kind of challenges and these industrial domains to all of you. So if you're interested, there's the URL for the website. Thank you very much.
One question, so duke it out.
I was just wondering if you could comment on the temporal aspect of these actions, and the one that you were showing didn't necessarily have any.
Yeah, so that's right. So the ones that we showed there, we actually got away without modeling any of the temporal aspects of it. We are doing test and simulation now where we are putting in temporal aspects. So we do have a sense, we do know, for instance, how long it takes, or roughly how long it takes to move from point A to point B, or at least model the fact that when we're starting to move from A to B, that takes some time. I can do other things like position the gripper, knowing the rack I'm going to get to then grab the object. So we are interested in doing more temporally based planning in this domain. But it was interesting how far we got without even having to go there.
It was exactly the same question. So perhaps one additional one, did you look at scheduling frameworks?
We actually didn't, and it's something to think about for future work. Our biases for planning coming from the planning community, so it seemed like these techniques would work well.
Okay, I think that's it for you.
Thank you.